Work and energy. Well, energy, everybody probably has a pretty good idea, or at least you probably feel comfortable with the word. Work means something really specific in physics. It's not just, homework is not necessarily work, physics-wise in the physics definition. But work and energy are interchangeable. So if I want to do some work on my mouse, what I do is I apply a force to it over a distance. And as I do that, when I do work on the mouse, I'm giving the mouse energy. So mouse doesn't really have any kinetic energy. We're going to get to kinetic energy in a little while. You've heard of that, right? Kinetic energy? It's energy of motion. So if I do some work on it, I'm going to put it in motion, and now it's got kinetic energy. But by doing work, I'm losing energy as I do work on this, and this is gaining energy. So if for some reason, the mouse could push me back, then it would give me energy, but it would have to lose some energy somehow. Work and energy are kind of interchangeable. They're going to have the same units, and you could think of them as interchangeable. Power, we use the term a lot, and I think it'll make sense to you. It has to do with how fast work is done or how fast you use energy. So a car with more horsepower, it's going to use energy faster. Oh, Riam. Oh, okay. Thank you, Riam. When I restarted my computer, I guess. Hey, did you not even see the video? Did any of you?
No.
Oh.
I didn't see.
That must have been really disappointing. Boring. Did you know I was showing a video?
Yeah, I don't see the side of the screen.
Okay. Never hesitate to butt in and say, hey, we can't see the video, or we can't see whatever. I'm sorry about that. When I restarted my computer, it stopped presenting. So my apologies. What else is down here? So we're going to get to this thing called the work energy theorem, which basically says what I've been saying, that work and energy are just kind of interchangeable. You can give something energy by doing work on it. And then we've got practice problems. All right, so work. The physics definition of work is the application of a force over a distance. It gets a little bit more specific than this. Work equals force times distance. The distance is the distance through which the force acts. So if I push my mouse, let's just say I'm going to apply 1 Newton of force, and I push it that far. So I don't know how many meters that is, maybe 0.08 meters. That would be the distance. Whatever force I applied to be the force, I'd multiply them together, and that would give me the amount of work. And the units for work are joules. Joules is also the unit for energy. It's a capital J. In the other class, I realized I might have not talked about this. Does anybody know why sometimes units are capital letters and some others are lowercase? Like meters is a lowercase m. Joules is an uppercase J.
Does it mean it has to do with energy?
No. Let me try to think of. Newtons is a capital N. Watts is a capital W.
Is it named after someone?
Yeah, it's named after someone. So this is named after a person. I think his name is James Prescott Joule. And when we get down to watts down there, that was named after somebody as well. All right, back to, so the units are joules. Going to do a little example problem. Oh, and I skipped this. I skipped the second word. Technically, the force in the equation is only the component of force in the direction of movement. And the dot product, like N dot M, reminds us of that. What that means is, I'll push my chair here and demonstrate this. So I'm going to push kind of down at an angle, and I'm pushing my chair across the floor. So I'm pushing my chair just in the X dimension, in the horizontal dimension, but I'm actually applying a force this way, which has got a little bit of vertical nature to it. But if I want to calculate the work that's being done on the chair, I have to take not my force, but the component of the force in the direction that it's moving. And that's the force that we use. So that's what is meant right here when it says, technically the force in the equation is only the component of the force in the direction of movement. So, child pulls a wagon 4 meters to the right, applying a constant rightward force of 10 newtons. How much work is done? Work equals force times distance. This is the easiest problem ever. Force, 10 newtons. The distance, 4 meters. And you could call it 40 Newton meters, but instead of that, we would say 40 joules. And to do that, the child would need to have 40 joules of chemical energy from food or something in order to do that kind of work. Now, number 2, another child pulls a wagon using a rope. And the tension in the rope is 20 newtons. The rope makes a 45-degree angle with horizontal. If the child applies this force constantly as the wagon travels 6 meters, how much work is done? We can't just do 20 newtons of force times 6 meters. And it's because we've got to use the component of force that's in the direction of movement. So the wagon's going to go this way, but the force that the child is applying is this way, and this angle is 45 degrees. So if this is a 20 Newton force and the rope is at a 45-degree angle and the cart goes 6 meters, how do we get the force that we actually need? We can't do 20 times 6. How do we find the force to multiply by 6? Which trig identity would we use? Sine, cosine, or tangent to get the force in this direction? Cosine, yeah. So we could, instead of just using this tension, we can break the tension up into the x component. That's the one we need. And then we don't really need the y component. So this is the one. That's the force that we need. And that's going to be cosine of 45 degrees times 20 newtons. And it should be about 14.1. So this is the force that we use, the component of the force applied by the child that is in the direction of movement. So I guess if you were to ask the question, how much work does the child do versus how much work is done on the wagon, maybe it would be different. But I think the best way to state this is how much work is done on the wagon. So we take this force, multiply it by 6 meters. And that comes out to 85 joules, about. Check my answer as I go. Yep, that's good. So work is pretty easy, and it kind of makes sense. It's a sensible sort of definition. Power is the rate of work. So if you had one child who pulled the wagon this far in 1 second and another child who took 15 seconds to do the same thing, they would have done this probably the same amount of work, but they'll have, well, assuming, no. I can't really say that. Well, if you did the same amount of work in different amounts of time, whoever does it faster has more power. So it's the rate of work. And the formula for power is work over time. It was pointed out last class, there are an awful lot of W's now. And how do you know which W is which W? I don't have a good answer for that. You just have to think about the context. If you're calculating power, it's the rate of work. So it's work over time. If you're trying to find, if you're drawing a picture of somebody and you're thinking about the normal force and you're thinking about this, well, that's weight then. And when we actually calculate power, the units are going to be watts. So the units are going to be a W. There's just going to be a lot of W's. Just going to have to deal with it. If if you don't know what kind of a W it is, you can ask me and I'll tell you if I can. All right. So the units for power that we use are watts. A watt is a joule per second. So if you apply a 1 Newton force, if you have a little block and you push it to the right with a force of 1 Newton, and you do that for a distance of 1 meter, that will be 1 joule. And if you do that in 1 second, you will have used 1 watt of power to do it. A 100-watt light bulb uses 100 joules of energy every second. Okay, 60-kilogram student climbs 12 meters up a vertical rock in 50 seconds. This is actually, it seems kind of straightforward, but we may get tripped up in this. This is a tricky situation. Now here's the student, and this person is climbing upward. It says the student's speed is constant. That's super important for being able to do this question. We want to know how much work the student did. And clearly we're going to use the force times distance formula. So what do I use for a force? Weight. Yes. Now, exactly why this makes sense, if you think about it too much, it might confuse you. But here's essentially what's going on. The weight of the person that the student is pulling him or her downward. And there's this other force, we'll just call that the climbing force, whatever it is, whatever force is propelling the student upward. And if these two are equal, what's the net force? 0. And what would the acceleration of the student be? 0. So is this okay? Can you climb up a wall without any acceleration? If the speed is constant. So yeah, if this person's climbing up at 1 meter per second and maintaining that the entire time, then the acceleration is 0. The force that's pushing them up is equal to their weight. So this is all good. So yes, this is how it should be. So the force that's applied to the student, that's pushing the student up, is going to be, I'm just going to make a little note, mg. I'm going to substitute in 60 kilograms times 9.8 meters per second squared. That's the weight of the student. And then the distance is 12 meters. So I get 60 times 9.8 times 12 is 7,056. And what would the units be? Joules. Yep. So it takes basically 7,056 joules of energy to make this happen. And jumping way ahead to something we're not going to talk about yet, what's happening is that the student is gaining potential energy. Have you heard about potential energy before? So he or she will have this much more potential energy than the student had in the beginning. But no more kinetic energy, which we'll get to in a moment too, because the velocity is the same. All right, the average power output in watts. So power equals work over time, and in this case, the amount of work is 7,056 joules. And it says that the time is 50 seconds. So 141 watts. How does that compare to a light bulb? Yeah, so an old incandescent light bulb, the kind that when you have ideas, it comes on above your head, and it's got a filament inside, just a single filament that's made out of tungsten, and Edison invented this kind of thing. A 100-watt bulb is pretty good for a average size room. So this would be like a light bulb and a half worth of energy. So if you were at a science museum and you're riding one of those bicycles and making light bulbs come on, this would be lighting up 1.5 light bulbs maybe. Today though, I've got light bulbs that are just as bright, but they're LEDs, so they're maybe using 5 or 10 watts. I don't know. Does anybody use LEDs in your house? Yeah. So it's light bulbs are so much better now. Those compact fluorescents that were popular 10 years ago, oh, those are awful. You seen those? The swirly kind? They're pretty, but they have mercury in them, so they're really like, you know, regular fluorescents. You got to be really careful about breaking them, and then when you do, you're probably paranoid about mercury. All right. So next question: how long would the climb have taken? So this 12-meter climb took 50 seconds with this many watts. How long would it have taken if the power output had been 1 horsepower? Here's the conversion: 1 horsepower, 746 watts. It's like 7.5 light bulbs per horse. I don't really know where people arrived at that, how they hooked up horses and how they came up with that number, but that's what a horsepower is. So I can use the same formula, power equals work over time, except now instead of this much power, I'm going to plug in 746 watts, which is 1 horsepower, and see how long it takes to do the same amount of work. The work would still be the same, 7,056 joules of work. So power equals work over time. Now we've got more power, so you cross multiply, we get T times 746, and then divide both sides by 746 to get T. It's going to be about 9.5 seconds. So 10 seconds to climb that wall using 1 horsepower, 12 meters. I don't know if that seems high or low or about right. Next thing, energy. We've basically been talking about energy the whole time, really. Work is equivalent to energy, and power is the rate at which energy is used or at which energy does work. And then energy can be thought of as a... Oh, okay. I thought this said energy can be thought of as equivalent to energy. It can be thought of as equivalent to work. When work's done on an object, the object gains energy. When work is done by an object, the object loses energy. The work energy theorem states that the net amount of work done equals change in kinetic energy. And kinetic energy is energy of motion, and the formula is 1/2 mv squared. So when you go faster, your velocity goes up and your kinetic energy goes up. If you have 2 objects with the same velocity but one's got a bigger mass, the bigger mass one is going to have more kinetic energy. So it's a function of mass and velocity, and the velocity is squared. So back to this. If you do work on something, like I was saying with the mouse earlier, as I do work on this, its kinetic energy changes. Doesn't have any kinetic energy right now, and I start to give it kinetic energy as I apply a force over a distance. Now something else, as I push this, something else is doing work on it. Otherwise it would still be moving now. What else is doing work on it? Friction. So as I push it to the left, friction's pushing it to the right, and friction is doing work, but it's going to be the opposite direction. So really, let me push it like this. So my push is positive, but friction is pushing negatively, and as I increase the kinetic energy, friction decreases it. All right. So let's just do some example problems. You can see how this work energy theorem is helpful. One of the really nice things in this unit, we're going to be able to go back now and look at problems that we did in other units and find much simpler ways to do them. We won't have to use as much kinematics. We can get around using kinematics and Newton's second law. First, there's this bit about calories, what calories are. I asked the other class, they said they have done this in chemistry. So you've converted from calories to joules back and forth? All right. So a calorie is 4.184 joules. They're both units of energy. I don't know if they told you this in chemistry, probably did, but the person who came up with all this, I think the experiment was got some water, put some kind of paddles down in the water and turned these paddles really fast. Have you heard about this? And did some work. So the paddles apply a force over a distance, and it was shown that if you do, let's see, what's the relationship? 4.8 joules of work. No, I got that wrong. If you do 1 joule of work, that'll raise 1 kilogram of water by 1 degree Celsius. So by stirring this around and doing work on it, applying force over a distance, the temperature of the water goes up. And that's where the unit of a joule came from. It's the amount of energy to raise 1 kilogram of water by 1 degree Celsius. Food calories, you probably know this too. If you, later on, there's going to be a Snickers bar in one of the problems. And a Snickers bar has 260,000 calories in it. So it says 260, or at least when I made this problem up, Snickers were 260 calories for a normal sized bar. But the food industry, instead of using real calories, what they call a calorie is 1,000 calories, or a kilocalorie. All right, got that behind us. Number 4. So this is back to the work energy theorem. When a 1/2 kilogram water rocket is launching, it experiences an average net force of 400 newtons for a distance of 1 meter. By how much does the kinetic energy change during this period? So I see this kinetic energy change, and I think automatically this is probably going to be a work energy theorem kind of question. And the work energy theorem says the net amount of work done equals the change in kinetic energy. The net is really important. The net is saying so work is force times distance. The net amount of work is the net force times distance. So you've got to be really careful that you're not just choosing an individual force and multiplying that by a distance. It's got to be the net force. So in this case, we're given the net force on the rocket, so that's good. And we're given the distance. So I can calculate this. I can just say, I'm going to write some more steps. F net times distance equals the change in kinetic energy. And the net force is 400 newtons. And the distance is 1 meter. So that's going to be 400 watts. What would the units be there? How much is the kinetic energy going to change by? 400 watts, 400 meters. What are the units of? They've got to be the same. They've got to be units of kinetic energy or units of work. Joules. So joules are the units of energy, also the units of work. So this 400 joules of work was done on the rocket. That means it's going to gain 400 joules of kinetic energy. So it's got that much more energy now. Assuming that the rocket started from rest, use the kinetic energy formula to find the rocket's velocity after accelerating for that 1 meter. So I'm not going to write this out as a formula, but if this is the change in kinetic energy and the rocket started from rest, in the beginning when it was at rest, how much kinetic energy did it have? 0. And if it changed by this much, how much does it now have? It's got 400. So let's just, basically we can jump to, the rocket now has 400 joules of energy, of kinetic energy. So I'm just going to say KE equals 400 joules. And this is an application of the kinetic energy formula. So the kinetic energy formula is listed over here if you forget it. 1/2 mv squared. Oh, not 12. So I'm going to put all this together, set this equal to that. 400 joules equals 1/2 times the mass of the rocket times v squared. The 1/2 times 0.5 is just a quarter. So basically need to divide both sides by a quarter. But I'm going to multiply both sides of the equation by 2, divide both sides by 0.5, and that'll give me v squared. So this is v squared, take the square root, got 40. So v equals 40. So I think this was a lot easier. All I had to do to figure out the velocity of this rocket after it went 1 meter was to do 400 times 1 and then set that equal to 1/2 times the mass times v squared. If we did this the old way, using Newton's second law and then some kinematics, we'd have to take the force and the mass, and from those two we could get the acceleration using F equals ma. And then we'd have the acceleration, we'd have the distance, we'd have the starting speed, and we would have to put in basically the v squared formula. V squared equals v0 squared plus 2a delta x. And we could have gotten to it that way, but this is a lot easier. All right. Here's another one that I think will be easier this way. We don't have to use any kinematics. So we have a package, and it's a 2 kilogram package, and it's sliding this way. It's got a velocity of 3 meters per second. The force of friction acting on the package is 1 Newton. The question is, how far is it going to go? So it's going to go over here eventually, and it's going to stop. And I want to know what this distance is. To make a better picture, I want to show the force of friction, the 1 Newton force of friction. Which way should the friction be pointing? To the left, yeah. So here's the 1 Newton friction. So I could do this based on stuff we've done before. Just analyze, get the net force, see the difference in speed, do some kinematics, or we could use the work energy theorem. So let's see, I'm just going to write work net equals changing kinetic energy. So to get the net amount of work that's being done on this thing, it's going to be something times distance, some force times distance. I need to know the net force acting on this block. Can anybody tell me what the net force is? How many newtons in which way? This is just a block sliding across the surface. Its mass is 2 kilograms. Its velocity is 3 meters per second to the right. There's a force of friction that we know that's 1 Newton to the left. What is the net force acting on that block? Assuming that there's no air resistance. So to do this, you can't use F equals ma. We don't know the acceleration, so we just have to think of all the possible individual forces acting on it. We know one, friction. What's another force that's acting on this? Exactly, there's the weight, but it's equal to the normal force. So in terms of contributing to the net force, those two cancel out. Is there anything else? So is there anything pushing it still forward? No, it's got some momentum. It's going 3 meters per second, and that's slowing down, slowing down, slowing down, but there's nothing pushing it to the right. So there's really, the slide itself doesn't have any force. Is there anything acting on it? Anything pushing or pulling other than the friction and these two forces? That's it. We're done. So the net force is the friction. I'm just going to write that over here. Just a net force in this case equals the force of friction, which equals negative 1 Newton. Why negative 1? Because it's to the left in my diagram. If 3 meters per second is positive, the velocity's to the right, then friction's got to be to the left. So I can write the net work done on this just as force times distance. The net force is negative 1. And the distance, I don't know. That's what I'm looking for. So that's what we're going to solve for. And yeah.
Can you explain the net force again? How you got
Yes.
to negative?
How I got to negative 1?
Yeah.
So in the problem, we're told that the force of friction acting on the package is 1 Newton, and we're told that the velocity is 3 meters per second. So that means it's moving to the right with the velocity of 3 meters per second. This is just a little arrow, smudgy, messy arrow showing the motion of it, 3 meters per second. That's not a force. In fact, I'll just erase that. So, but it's going to the right. Maybe I'll put it over here. V equals 3 meters per second. And I'll put this force back. So if anything's moving to the right, friction always opposes the motion. So the friction's going to be to the left. So there's one force acting on it. The only other forces I can think of that could be acting on this block are its weight, which is pushing down, and the normal force of the surface pushing up. But it's not going up or down, so I know these two forces are equal. So when I add up all the forces that are here, this plus this is 0. All I'm left with is this, and it's to the left. So the net force, what I get if I add them all up, is the force of friction, and it equals negative 1 Newton.
But if it's sliding across the surface, shouldn't there be, and like since friction is supposed to oppose like whatever force is pushing it to the right, why isn't there a rightward force that you're factoring in?
So no, friction doesn't oppose. That's a good point. And if I've said this, I misspoke. So friction doesn't oppose a force, it opposes motion. So if I slide this, I need a little more space to slide my mouse. If I slide my mouse along, this is sort of lackluster, but after it leaves my hand, it continues going there. And the reason it doesn't go forever in that direction is because friction is pushing back this way. But once it leaves my hand, there's no force pushing it that way. It's just the motion is that direction. So friction doesn't oppose forces. Friction opposes motion. If I put my two hands together and try to slide them apart, it's the relative motion that it's opposing. It's a force that opposes motion.
Okay. So the reason you don't have a right or like a force in the right direction is because friction is just opposing the rightward motion, not any force.
Yes. Now, in order for this whole thing to happen, somewhere way back in the beginning, something must have pushed it to the right. Otherwise, it wouldn't have that velocity to begin with. So if I showed you the prequel to this question, there would be a person standing over here maybe who's bowling, and they push this block and it goes sliding, sliding, sliding. And then when our problem begins, it's already sliding, but the question is just about what's happening to it as it slows to a stop. Nobody's pushing it anymore, and the entire time it's friction is pushing to the left. This is like the beginning of the year stuff. It's an object moving to the right, but accelerating to the left because there's a net force to the left.
Right.
And so if you move positively but you accelerate negatively, you slow down.
Yep. Okay, thank you.
Okay. So back to this. Now I can just wrap it up really quickly. So this is the work, the net force times distance. And the change in kinetic energy, I'm going to write it as, KE final minus KE initial. And one of those is really obvious and we know it. What do we know? The final kinetic energy or the initial one? What's the easiest one to... The what? The initial. We could calculate the initial, but there's the final one we don't even need to calculate. Why?
0.
Because it stops. So this is going to be 0 minus, and now for the initial we can do it. We just have to put in numbers. 1/2 times the mass, 2 kilograms, times its velocity squared. And this is pretty easy math because 1/2 times 2 is just 1. 3 squared is 9. So I get -1 Newton times D equals -9. So D ends up being 9 meters. Trust me on that if you do the workout. So I spent a lot of time talking about this, but once you get comfortable with this, the effort that you have to put forth is really minimal. You just multiply that force times D, and it equals the kinetic energy it started with. But if you use Newton's laws to do this, you would have to get the net force and use the mass to then get the acceleration, and you would have a starting velocity, you would have to find the acceleration distance, and this is a lot easier. So that's it for, we're not going to get into potential energy today. The problems to do are on pages 3 and 4, 1 through 5. 1 I think is kind of straightforward. 2 is kind of straightforward. 3, this is a ball hanging from the ceiling on a train, so any of you who didn't like this sort of thing, you're going to really not like this because it's more of the same plus some new energy stuff. 4 is just super easy. 5 is about a Ferrari accelerating and has to do with coefficients of friction. So, let's see, I guess we've got about not quite 20 minutes. If you look in Google Classroom, I've got a video where I go over my solutions. I've also provided my solutions. If one of the sets of solutions is just kind of messy like this, another one is better. This is all the solutions to number 1 and 2. And then I realized that I skipped number 3 and 4. So I have a separate page for 3 and 4 right there. So anyway, try to do those. If you work more than about an hour on them, just stop. We can discuss these tomorrow. Last class went a little faster, so they had a little bit more time. So I don't want to overwork you. Don't get too worked up about any of this. We'll clarify all this after break. I just didn't want to waste a day.
That was a good pun.
Oh, yeah. It's hard to stay away from the word work once you start teaching about work. So that's it. People who are in the